Okay, so welcome back. I hope you have solved the numerical problem, and as I said that you yourself have tried to see whether it is converging or not. But interesting thing is that this kind of method is very impractical for hand analysis, because even for simple circuit, if you have to go through number of iteration, and as I said that based on the slope, the convergence may or may be there, or it may converge, but it may take more time based on this condition. So, it may not be a good idea to stick to this one. It is better to look out some other alternative. Okay, there is a small correction here. This is supposed to be VD3. Anyway, so let us move to what may be the practical method, or can we have a method to solve just by one step itself. Yes, if we consider the same numerical problem, namely if I consider the V in here, and then we do have the resistance of 10 k, and then we do have the diode here, and then if we observe the corresponding output, by considering one initial guess, and this initial guess, it is not just arbitrary. Typically, we know that if it is silicon diode and if the diode is on, the drop across this diode is roughly 0.6 volt. And with this guess, if I consider V d equals to 0.6, the value of this I r you will be obtaining, it is 10 volt minus 0.6 divided by 10 k. So, what you are getting here, it is 0.94 milliampere. Now, if you compare our the previous numerical value, which it was close to, if I recall correctly, 0.94023, something like this milliampere. So, if I compare this value after third iteration you obtain versus this one, what we have, it is the amount of error, it is in fact less than I should say 0.03%. So, we can say 0.03%. So, then just by one step itself we can find the solution. This is of course one indication that how we are trying to get a practical method by the virtue of guess and proceed by one iteration. But then some people may say that no, I do have a diode, it may be silicon diode, but I know that its diode drop, it is roughly 0.7, and if you use instead of 0.6, if you use 0.7, then also if you see the corresponding value of this I r is 10 minus 0.7 divided by 10 k. So, this is it is coming 0.93 milliampere. Of course, it is slightly different from this value. It is not as close as this one, but still if you compare this value and this value, I should say this amount of error, it is in the order of just 1%, slightly above 1%. So, even with this much of I should say guess, we are getting some solution which is falling within this accuracy level of accuracy, and most of the time for hand calculation this may be sufficient. Most of the time for engineering problem, if it is well within 10%, we may say this is sufficient. So, this gives us one indication that probably we may have some practical method to replace this diode by a something called some model. So, what is that model? We may consider if the diode is on, drop across this diode, it is maybe around 0.6 or 0.7, and let you call this voltage is V gamma. And but then if depending on the current level, the voltage drop across this diode, it may not be remaining same. So, whatever the little dependency of the voltage and current is there, that may be represented by probably another element called R on. So, depending on the context, we may say that either this is 0 or it may be non-zero, and typically the value of this R on, it will be small. So, what we are getting is that by replacing this diode by this simple circuit, of course, here we have considered this is equal to 0. That is why with this whatever cut-in voltage of 0.6, we are directly getting this value, and if you are plugging in this meaningful value of this R naught, you will be getting even more accurate result. So, depending on the situation, most of the time we may be using this kind of model for the diode, if the diode it is in on condition. On the other hand, if the diode it is in off condition, we may use different model. So, we may say that the resistance of the diode in off condition, it may be quite high. So, in that case, the diode may be replaced by a simple resistor, where this off resistance, it may be quite high. So, it may be even higher than 10 mega ohms or maybe beyond that. So, we do have two models, one is this one, another is this one, and both of them are, you can say, linear. So, we may say depending on the condition of the diode, we are going to replace by linear model, but then single linear model is not working. We do have piecewise linear model. So, we do have one model here, we do have another model here. This slope, it is representing finite value of this R on, and this is the cut-in voltage, and this flat line indicates that R off, it is very high. Okay. So, we can say that this is the model we will be using instead of using our exponential relationship for practical purposes. So, instead of this exponential relationship, we will be going for this piecewise linear model. And let us see how this model it can be used. So, let us move to the piecewise linear model more detail. So, as I said that if the diode is on, we may replace this diode by simply on resistance in series with V gamma called cut-in voltage, and this R on. So, what is this R on? How do we get that? The change in diode current with respect to diode voltage is essentially this is 1 by R naught, R on, and if you see this derivative of the I d with respect to V d, that gives us I d divided by V t. So, depending on the value of this current and depending on the value of this V t, you can easily find this voltage, and as I said that V gamma you may be having a good guess around 0.6 or 0.7, that may be sufficient. On the other hand, if the diode it is in off condition, as I said that this will be replaced by the simply off resistance, and the value of this resistance again this can be obtained by considering change in I d with respect to V d in cutoff region. So, now what we can say that if I replace this I d by the I naught e to the power V d by V t minus 1, and so if I take derivative of this expression of the current with respect to V d, what we will be getting is we will be practically getting I naught divided by V t. Particularly this will be getting at say V d equals to 0. In fact, this is also valid if the V d is negative, that means in reverse bias condition. If the V d is higher and if it is becoming comparable with V t, of course, this will be deviating from this number. but just to get a sense of what is the value of this resistance which is reciprocal of this. So, which is V t divided by I naught, it is 26 millivolt divided by 10 to the power minus 13 in this case. Right. So, which means that it is 26 into 10 to the power 10 ohms, that is very high. So, we can say for all practical purposes in reverse bias condition it is very high, even if say diode voltage is say positive, but as long as it is less than this cut in voltage, then also we may say that this resistance it may be remaining in the order of tens of mega ohms. So, that is the circuit model, and as I said that these two representation of the diode is essentially we do have exponential equation is getting replaced by piecewise linear model. So, we do have cutoff region and then we do have the okay. So, let me we do have the on region and we do have the cutoff region here. So, based on these two pieces we can simplify the circuit. So, let us see how this piecewise linear model can be practically used for the previous example circuit. So, let us see the, as I said, let us see the application of this simple model. Let me redraw this circuit by replacing this diode, assuming this V in is higher than cut in voltage and hence the diode is in on condition. So, the diode it will be replaced by the equivalent circuit in on condition. So, we do have the V in here connected across this diode and we call this is V out. In fact, we call this is cut in voltage and the voltage drop across the series connection, namely V gamma and drop across this on resistance R on, together it is nothing but the diode voltage and this is the R. So, you may say that this behavior, this part is essentially diode it is getting replaced by piecewise linear model, essentially this piecewise linear model. So, now if I replace this diode characteristic in this form, so how do I find the solution? Instead of going through this iterative method, can I get even a straightforward straightforward single step method. So, here again we may say that I do have pull up element and its characteristic is given here and the voltage here it is V in, slope here it is 1 by R with a minus sign, and then if I say that this characteristic lower element characteristic it is nothing but this one, where this part is V gamma. Now, if I know this slope then it will be well and good, but in case if you do not know, probably you can assume that this is V gamma and then you can find the corresponding current here, and from that using that ID current you can calculate this R on equals to whatever the current you will be getting here, say I R divided by V t inverse. So, that gives you the slope here. So, that is whatever the I R you will get divided by V t, that will be giving you the slope. So, if you know this point, if you know this slope, then you can find the intersection point of the two linear lines. So, that is how this equivalent circuit it can be used. Now, next thing is that how do I use this simple model in case this input voltage is changing with time and using the same equivalent circuit. So, if this voltage it is say getting increased to some other, this input voltage it is getting increased, we can say that slope remains the same, but then the corresponding pull up characteristic or rearranged characteristic it is getting shifted up, and we may say that this may be new V in called V in 1, this may be V in 0. So, now the intersection point is getting moved up here, and the corresponding output voltage instead of this one, now it is getting changed to whatever V out or V d, whatever you say, it is going to V d 1 from the previous one. Previous one it was V d 0. So, likewise, if the V in it is changing to some other value, say lower value with respect to the previous V in, the corresponding the cutting point of the pull up characteristic, rearranged characteristic, now it is shifted to some lower value called V in 2. So, now we do have V in 0, V in 1 and V in 2. So, the corresponding output here it will be V d 2, and all these V d's are essentially same as V out. So, now for different values of this V in, if I try to see what will be the corresponding V d or V out, what I will be getting is input to output transfer characteristic. And if you see here pictorial view, as I said that pictorial discussion. So, if I change this V in from say this value to this value and this value, what I am getting is the corresponding V out or V d, it is changing slowly. So, if you see that the amount of change here, it is very small compared to whatever the changes are there. So, even though V in is changing over a wide range, the corresponding output change or V d change it is very small. That is mainly because slope of this line it is very high. In fact, theoretically if I say that if this line it is vertical, this line it will be horizontal, indicating that if R on it is 0, at the output you will get only V gamma. And so, you can say that input to output transfer characteristic is like this, but it will be this transfer characteristic it is valid as long as the diode it is in on region. So, if the voltage in the input voltage if it is less than V gamma, on the other hand then load line or you can say the pull up characteristic it will be like this, and then it cuts the diode characteristic at this point. So, if you change this V in now, say instead of this one if you are changing the V in here and so, the corresponding V out will also be equally changing. So, in other words, if the V in it is less than say V gamma, then input and output they are having the same value. So, the input to output transfer characteristic of the circuit. So, if I so this V d is nothing but as I said V out. So, input to output transfer characteristic it is having two segment, one is this one, another is this one. This is mainly coming because of the two pieces of the diode characteristic, and this part it is very small, having very small slope representing the high slope of this line, and this is having fairly good slope. So, that is the input to output transfer characteristic you can say. Now, having said that if this voltage it is changing with time, we may be having different way of changing this voltage. So, you may say that this voltage may be having a DC value and then it may be having the variable part. So, which means that we may keep the DC voltage maybe somewhere here, and then we may vary this input with respect to that, either maybe in sinusoidal form or it may be triangular form or whatever it is. And then the corresponding output, whatever the output you will be getting, that can be directly obtained from this transfer characteristic. In other words, that using this input to output transfer characteristic, you can find what will be the input to output relationship. So, that is what we will be discussing now. Instead of varying this input voltage arbitrarily and maybe over a wide range, if we restrict this variation within this range, and if the variation is having certain pattern, then you can say that this linear segment, it is also suggesting that at the output you will also be getting the similar kind of pattern without having much distortion. On the other hand, if the variation it is large enough and if the diode is entering into the other region of operation, then of course, the signal at the output it may be having getting distorted because of the highly nonlinear nature. So, for the time being, let me consider a situation where this signal variation it is getting restricted over this linear range. So, let you move to the corresponding example, where the input voltage basically this is the same circuit. Now, we do have the input, it is combination of it is having combination of DC part, namely capital V in and then the small signal part. So, we do have the small signal part here. So, as you can guess that if I analyze this circuit, you will also be finding the corresponding V out, which will be having two component. One part is corresponding to DC part, another part it is corresponding to small signal part. So, before we go into the actual expression, let me redraw this circuit, namely replace this diode by the corresponding equivalent circuit. So, we do have the small signal, we do have the DC part, and then we do have the pull up element, and then we do have the diode part, and this diode part it is having cut in voltage in series with this R on. So, this is I should say equivalent circuit. So, now we can say that the actual circuit is getting converted into equivalent circuit, and where what we are doing is this model, whatever we say this working model we are using for the diode. So, we do have R here, same R, and we do have the R on here, we do have V gamma. Now, if you analyze this circuit, if I consider these two together, it is V capital in having both DC part and the small signal part, and if you see what is the corresponding output, I think you yourself can find that V out equals to it is having V in multiplied by R on divided by capital R plus small r on plus V gamma into R divided by capital R plus R on. Basically, you are finding this output voltage by superposition theorem by considering this one first, making this 0, and the second part is making this part 0, and you are keeping this V gamma. Now, within this V in, as I said that it is having both DC part and the AC part. So, if I rewrite this portion in terms of this capital V in and then a small signal part small v in, what we will be getting is you can say that this is V in R on divided by R plus R on plus V gamma into R divided by R plus R on. In addition to we do have V in R on divided by R plus R on. So, this part you may say that this part it is coming from the DC part, and the cut-in voltage of the diode you may say that it is not changing, but this part probably it is changing with time and probably it is carrying a signal. So, this V in may be function of time. So, this V out you may say that it is having two parts, namely V out capital plus small signal V out. So, this small signal V out it is basically this part. So, we can say that capital V out or DC part is having this expression, and the small signal V out, small V out is R on divided by capital R plus small r into V in. So, you may say that this part it is transfer function of the system, which is transforming this input maybe in time domain, this is also maybe in time domain, but whatever it is, the signal it is getting reflected to the output. And if you are not changing this point, this operating point, you may say that the corresponding R on practically remains constant. So, we may say that the gain of this circuit remains constant. So, let me see the corresponding input to output transfer characteristic curve, and let we reinterpret what other things are there. Please remember that this small signal part and then DC part in the next slide. So, let me rewrite this V out part. So, we do have V out is having DC part. I am just simply denoting this is V out. So, you may assume that this is function of capital V in and V gamma and so and so. And in addition to that, we do have the small signal part, which is R on divided by capital R plus small r into V in, right. So, this is what we already have. Now, what is the interpretation in the transfer characteristic curve? So, you may recall that in the input to output transfer characteristic curve, if I say that this is the V in having both DC part as well as the small signal part, and along the y axis we do have the V out, and we say that the transfer characteristic curve it is fairly linear, may be having a small slope as long as this is not exceeding this V gamma voltage, then we are safe. And if I say that we do have V in probably V capital in, with respect to that we are applying some small signal V in. So, over that with respect to capital V in we are applying V in and changing this the corresponding V in. What is the consequence here? At the output corresponding to V in you are getting V capital out, which is of course, it is function of V in and R and then R on and V gamma and so and so. And in addition to that, what you are getting is because of this small signal applied at the input, we are also getting corresponding output. So, you may say that here we are getting small signal output, and this small signal output it is given there. Now, many a times for analog circuit, we may be keeping this point, this DC part constant, In other words, we like to keep this point constant, and then we like to apply this as signal. So, it may be sinusoidal, it may be non sinusoidal or whatever it is, and we like to keep our concentration only over this range. So, if you vary this signal here, we will be getting the corresponding output here, and we like to see the relationship between the small signal input to small signal output. So, what does it mean is that our main interest for analog circuit, instead of really seeing this much of DC shift and all, we may be rather more focusing on V in to V out, small signal V into V out characteristic curve, which means that we are basically concentrating on this part. What is this part? This part of the input to output transfer characteristic curve, it is getting shifted to the origin of this new graph. So, we can say that operating point is getting shifted to the origin of this characteristic curve, and the line segment it is getting retained, it is retained. Now, this characteristic curve, so here if I apply input signal, naturally I will be getting the corresponding output here. Okay. So, here while we are retaining this DC part, it is referred as large signal, input to output transfer characteristic curve, and this is referred as small signal transfer characteristic curve. So, what is the advantage here? First of all, this characteristic curve, it is not going through the origin, whereas this is going through the origin, and we are keeping the circuit, in fact, the analysis probably simpler, because we are dropping the DC part. Okay. So, this whatever the translation of the characteristic curve from large signal to small signal, it is circuit wise, it is you may say that the original circuit we are representing by another equivalent circuit called small signal equivalent circuit. So, this translation of the transfer characteristic curve is basically circuit wise representing the circuit in a simpler form. So, let us see what is the simpler form. So, now we do have some notion called small signal equivalent circuit. So, to start with, we do have the signal in series with the DC part, and then we do have the resistor, we do have the diode part along with the cut in voltage, and then we are completing the circuit. So, this is what we said, it is the large signal equivalent circuit consisting both V gamma and R on. Now, whenever you are talking, so this is the large signal. Now, let us see what is the small signal. So, in small signal, what we will be doing is that we will retain this part, we will retain this part, and the DC part. So, whatever you say V in, V capital in, we like to remove it. We like to remove this one, we like to remove this one, and we like to retain only this one. So, the left out circuit, what we will be having here, it is the signal part, the same resistor R, and then we do have the R on, and the corresponding V gamma, it is completely dropped. This is V in, and whatever the corresponding output we will be obtaining here, note that this is small V out. Here we are having capital V out containing both DC as well as AC, whereas here we do have only small signal part. So, this is referred as small signal equivalent circuit, and as you can see here, what is the what are the rules? The DC part we are making it 0. The DC voltage whatever, even though it is coming from the device, we are dropping to 0, and rest of the things we are retaining, and we are retaining of course the small signal part. So, that is the rule, and graphical interpretation what we said, it is translating the large signal transfer characteristic curve to different graph, and the transfer characteristic curve it is going through origin. This is a very vital point, that it is going through the origin, which means that this circuit is basically representing linearized version of the original circuit. Even though this circuit it is nonlinear, but whatever the characteristic we are getting and the equivalent circuit we are getting here, it is nothing but linearization. So, whenever we are talking about small signal equivalent circuit, I should say that it is linearization of the large signal equivalent circuit. Now, we do have whatever we have discussed is that the original circuit, from that we obtain large signal equivalent circuit. This large signal equivalent circuit, it will be helping us to find the operating point, and in fact, that operating point helps us to find the value of this R on. So, definitely that is important. Also, we have to check whether we are in the linear range of large signal characteristic. Probably you can find what may be the limit up to which this linear characteristic is valid, and then we move to small signal. So, it is having importance, large signal equivalent circuit, it is having importance, but once you are very sure that this point it is a good point, and then better we translate to the entire circuit into a small signal equivalent circuit or linearizing the circuit. Yeah. So, as I said that we are linearizing the circuit, and we have enlisted what are the different advantages. Note that we are linearizing nonlinear circuit with respect to the operating point or question point. So, first we find the operating point, and then we are basically linearizing the circuit. So, it is expected that once you linearize, probably the obtained circuit is simpler. We already have seen that. And most important thing is that this will simplify the analysis, and the other vital point is that since the input to output transfer characteristic it is going through the origin of our small signal transfer characteristic. So, superposition theorem it is valid, and that is very vital to simplify a circuit whenever you do have multiple signal sources. So, these are the important advantages, and that is why for analog circuit we always do find the nonlinear circuit, then we move to small signal equivalent circuit or linearized circuit. And however, you need to be very careful, word of caution that validity of the linear circuit you have to be maintained, and the signal level should be such that we should restrict our voltage and currents within the linear range of operation. I think what you can do it is probably you can try to take this numerical problem and you can try to solve this. So, I have framed this numerical problem slightly, I have changed this voltage and rest of the things I have kept as is. So, what you have to, I think you yourself can find. So, you need to find this ID and V out by iterative method we already have discussed, and also practical model method considering V gamma equals to 0.6 volt and R on, probably you can calculate the value of R on which is non-zero, and from that you can find what will be the corresponding V out. Of course, that will be slightly different from V gamma, and then you can draw the small signal equivalent circuit. You can find the small signal V out. So, this is a small signal V out for small signal input voltage here. So, this small signal input voltage it is given there. You need to find what will be the corresponding small V out. So, there may be two approaches. One is directly you can use large signal model. You will be finding that it is bit tedious, even though it is simplified model of the diode has been used there. and then you can see how easy to use the small signal equivalent circuit. So, in this part of our discussion, what we have covered, it is basically we are analyzing, or we have analyzed nonlinear circuit, diode circuit as an example to find its solution. We have discussed two generalized method. One is, in fact, both of them are essentially same. One is pictorial representation, and where we have discussed how to rearrange the pull up characteristic to get it suitable in combining form with the pull down part. And then the method of the iterative method of finding the solution. Then in the second part, we have gone into the practical method of finding solution, namely using guess and solution, one step solution, which suggests that it is better to use some simpler model, working model of the diode, namely piecewise linear model. And that model we have discussed with the same diode circuit, and then we have gone into linearization of the circuit. Basically, nonlinear circuit we can linearize, and we have discussed about a notion called small signal equivalent circuit, and it's how we obtain the small signal equivalent circuit. I think that is all I do have now. Yeah, so I think we will be moving to the next topic in the next class. Thank you.